Setting up the meeting. And there we go. We are now live on YouTube, or at least, but I'm probably the only person they can see. So we'll go ahead and get started. Welcome everybody to our June 1st, 2023 meetup for GDG Dallas. Where's the controls? There we go. I am one of your hosts. My name is Luke. Stacy and Joaquin are also on the call tonight. It's great to have them here. We are a team that tries to bring you great meetups every month. Just want to mention our Zoom for the evening for this remote virtual meetup is provided by BottleRocket and allows us to do cool things like record and stream to YouTube. And so it's really nice. Common question at all meetups is, where are the bathrooms? We have this handy diagram. This is you. You're probably at your computer. The bathroom is somewhere behind you, perhaps. You'll have to ask around your specific location. I can be no more helpful than this. We have a website. It's gdgdallas.com. Right now, that pretty much just redirects to the meetup site or maybe the community dev site. If you have any interest in helping us work on that, just helping set up a page, we'd love to have your help. We also have the official GDG site, which is over at the gdg.community.dev/gdg-dallas. That's kind of the main official site. We also have a meetup site, which is kind of our legacy site, but we try to post in both places for legacy members and new members. We're trying to migrate towards the official site. So we have time. We do have a Slack, so you can join that, stay connected. In the meantime, again, we try to post some announcements there, and it's kind of a good way to stay connected to the community. If you want to connect with people at the meetup, that can be a great way to do it. And we have, of course, we have a YouTube channel where we're live streaming right now. And it has a lot of videos there. You can look back and kind of see the archives, either as the live archives or the uploaded videos archived. Take a look at that, look through the content. Some of them get hundreds of views. Quick look through, yeah, several hundred views. We've got some that have thousands of views, so pretty impressive. So take a look there. Of course, we have all the socials. Well, maybe not all the socials because there's a lot more than this, right? But Twitter, Instagram, and LinkedIn. Follow us on those to keep up with what's going on. And mention we have one other meetup currently planned. It's not live. You can't RSVP for it just yet. We're still working on getting the description and that kind of stuff worked out, but it's something that we'll be doing June 15th. And the plan is to do this one hybrid. So we'll have an online Zoom or something to join, as well as an in-person for people in the Dallas-Fort Worth area. That'll be at the BottleRocket offices for people in Dallas. That's in Addison off the North Tollway at Beltline area. Some people kind of know where that is, so that's the only reason I mention it. And Harish Patel, he's actually a coworker of mine, a longtime Android developer and all-around great guy. And he's been doing a lot of work with Android widgets and the Glance framework, all the new stuff with Compose that they're doing. And so he's really been analyzing that and building a lot of stuff. And he just wants to present his findings and kind of how useful some of that stuff is across all the different platforms. So keep an eye out for that. Like I said, it hasn't been posted yet, but when it gets posted, if you're on any of the groups, you should see that one pop up. And organizers, if you're interested in helping with GDG Dallas, helping put together, other talks, you don't have to speak yourself. Maybe you just want to help build the community. You just like hosting meetups. You like talking in front of people and making announcements about how you're looking for more organizers to get really not redundant, but what's the word? Recursive. I'm going to get really recursive. So I'm going to make an announcement about how you can join and make announcements about making announcements about joining. But if you'd like to do any of that, feel free to talk to us, message Stacy, Joaquin, or me, either tonight during the meetup or after the meetup. There's some different ways to do that. You can send private chats through the Zoom. You can basically send a message directly to an individual. So feel free to do that during the Zoom if you'd like. Also, if you'd like to speak, we're always looking for speakers. You don't have to speak next week. You can have some time. If you say, oh, I'd like to speak in July or August or September, that can be great for us because it's great to have things scheduled out. So if you've got stuff that you'd like to share, maybe it's something you're learning, maybe it's something you've been doing at work and you'd like to just share, maybe abstract out, take out all the kind of work specific stuff and just share kind of some of the technology. Those are really popular talks. People love to hear about what other people are doing and just cool technology. So keep that in mind. And then this is the audience participation portion of the announcements where we ask if anybody has any announcements that they'd like to share. Maybe this is a meetup, maybe it's a hackathon, maybe it's just another, another meeting of, kind of technology stuff. Maybe you're speaking somewhere else at some other meetup and you'd like to promote your talk here. That's perfectly fine. So if you'd like to come off mute and I will watch the chat. I've been told I have the great skill of awkward pauses. Like I can let a pause go way past when it's awkward. And so I'm willing to sit here and wait. But I can also fill the time and move on when I'm giving everybody a chance. I know finding that mute button can be hard. Joaquin, did you have anything?
Just saying that nobody appeared to have anything.
Yeah, move on, buddy. Move on. I can.
Yeah. Let's go.
Okay. We will try to have notes, and of course, like I said, we're live streaming, so you should be able to go back and review. You could even go over and check the live stream and back it up a little bit and rewatch parts, live if you wanted. So feel free to do that. But if there's any notes from this, we'll try to share those out either, through some various means. So I try to post them in the YouTube description or something like that. And now, what you've all been waiting for, our feature presentation. I will go ahead and stop sharing. And I will introduce our speaker, Gonzalo. Gonzalo is a backend developer from Madrid. He's currently based in Pittsburgh, Pennsylvania. And a couple of years ago, he started down a rabbit hole of noise and frustration to try to understand what all this talk about reactive is about. But when he's not coding, he's probably playing music, watching cartoons, or wasting his time on old video games. His words, not mine. I don't know if I'd call that a waste of time, but that is our presenter tonight, Gonzalo. And since we have a organizer that speaks Spanish and Gonzalo is from Madrid, we'd like to do an intro in Spanish. So take it away, Joaquin.
Yeah. Ok, bueno, pues básicamente lo mismo que ya ha dicho Luke, pero en español. Pues Gonzalo es un compañero mío de Singular. Él es un backend developer de Madrid. Y bueno, ahora vive en Pittsburgh. Se puso a explorar esto de la madriguera de conejos, ¿no? Esto del caos y de cómo aprovechar el fallo y todo el manifiesto reactivo. Y bueno, está aquí hoy con nosotros para contarnos un poco acerca de todo esto. Gonzalo, muchas gracias. Y nada, adelante.
Muchas gracias, Joaquin. Thank you very much, Luke. Stacy, also for putting this together and for inviting me to talk. Okay, so let's see if I can share the screen. Okay. You guys are able to see it?
Yep.
Okay. All right. So yeah, thanks again for attending the talk. I hope it'll be of some value to you. So today we're going to try to break down a few ideas and strategies behind the concept of failure and its role in reactive system. A little bit about myself. Well, Luke already and Joaquin already said a little bit about me, but yeah. So my name is Gonzalo. I'm originally from Madrid, Spain. I'm currently working as a backend developer at SNGULAR in Pittsburgh. And yes, about like 3 years ago or so, I got interested in reactive systems and reactive programming. And that's why I got into this line of talks. So let's see. Okay. So I divided this talk into 4 sections. The first one is going to be a brief summary of what reactive systems are. And second, we'll go over some fundamentals about failure and errors in reactive system. Then we'll talk about some of the common strategies and best practices that we can implement. And finally, we'll go over some case studies related to the content of the talk. So this talk is about failure in reactive systems. And I'm going to try to make the case for, as it is explained in the reactive manifesto, why we should embrace it. So first, let's refresh our knowledge on what reactive is, also following the definition provided by the reactive manifesto. A system is considered reactive if it's responsive, resilient, elastic, and message-driven. It's responsive if it's consistently able to respond in a timely manner. It's resilient if it's fault tolerant, and it's able to handle failure gracefully. It's elastic if it's able to scale horizontally and vertically. And it's message-driven if it's asynchronous and able to delegate failure as messages. So in order to meet these 4 requirements, the system must follow these other rules, if you will, which would be a stay responsive, accept uncertainty, embrace failure, assert autonomy, tailor consistency, decouple time, decouple space, handle dynamics. So they all sound good. They all add their own slice of wisdom. But this session is going to focus on just embracing failure, which is a large topic in itself. So let's see. First, a common misconception: reactive systems and reactive programming, they are not the same thing. When we talk about reactive systems, we are talking about a set of architectural principles. We went over them in the previous slide. But reactive programming, on the other hand, is just a tool we can use to adapt our code to be message-driven, but it's really not the same concept. Using reactive programming can help us build reactive systems, but it does not necessarily mean that our system is automatically reactive, if that makes sense. So what about failure? Failure is any problem that is preventing our system from operating normally. And it comes in different shapes, a lot of shapes. And after a lot of work of troubleshooting and firefighting and redesigning, we might think that we've done everything we can to prevent failure from happening, but in reality, we will never get there. Our system is going to fail. And when we accept that, when we embrace the fact that it's happening, no matter how bulletproof we think our system is, then we can start working on being prepared for it, designed for resiliency, for resilience. That's what will make our system truly robust. When failure happens, we want our system to be able to shake it off as quickly as possible. So the first distinction we are going to make is the one between what's considered a failure and what's considered an error, because both are unwelcome behaviors, but an error is an expected part of the system's operation, meaning that we will prepare the code so that these expected errors can be dealt with immediately. And once an error is handled and communicated, the system just continues to operate normally. An example of an error could be an error during input validation. If we somehow expect that the client could be using invalid data, then we need to explicitly code the error handling for it. But that's it. The service will remain operational. On the other hand, failure is unexpected. It prevents the system from operating normally. So it's disruptive in a way that the failing component cannot handle by itself. So until we have external intervention applied to it, the system won't resume service. Let's say that there's a defect that gets the internal state corrupted. The system is less likely to be able to fully recover from that. We'll use the next slide to elaborate briefly on the difference here. So this is an oversimplified representation of a service that books tickets. So in both examples, a user is trying to book a ticket. And what our system is doing is sending a request from our UI module to the backend. But in the first example on the left, we have an explicitly represented error. An error like this allows the service to provide degraded service instead of just failing silently. It can be communicated as a value to other processes, to other threads, or even over the network. Whereas in the example on the right side, we have an unexpected failure. The service is stressed with too many requests, and it will fail silently. In this case, the user will not receive a significant response of what went wrong. He will just get a poor user experience. And this takes us to the let it crash approach, because even undetectable failure should not influence the application. The system should continue to operate normally. So I'm sure at some point we have all been tempted to try to foolproof a service from every possible error. That's the defensive approach. But if we build our code to try to prevent, let's say, 100 error scenarios, then scenario number 101 will eventually get us. So we want to explicitly handle only expected errors. And when it comes to the unexpected, we just let the component crash. And when it does, a supervisor of that component will need to have the capability to shut it down gracefully and restart it as quickly as possible. So in this diagram, we can appreciate that this approach can be applicable to any kind of component in the chain, whether it's a function that fails and communicates to the service invoking it, or it could be a handler being used from a controller, or a microservice calling another microservice, or it could also be a bot taking care of a failure in one of its container. So one more time, a closer look on this. We have a supervisor, or an upper component, if you will, invoking or managing another component. If this component fails, instead of swallowing the failure and trying to do any kind of self-healing, we let it crash, and we let the supervisor take care of that failure. And at the same time, we are shielding other components from such failure. And now you might be thinking that nothing explained up to this point is really specific to a reactive system, and you would be right. But you are probably already following this approach regardless of the nature of your system. But let's get further and see how it all connects. Okay. Well, that's kind of the illustration of the pattern of let it crash that I was trying to explain before. So we have the supervisor invoking a component. The component fails. It immediately notifies that to the supervisor, and then the supervisor will take the necessary steps to enable the failing component back up again. So, okay, in order to keep our system responsive, we want to be able to fail fast. Let's not get stuck erratically trying to recover. Let's just crash, restart, and carry on. If our system is going to fail, and it is going to fail, we want it to be able to be fully operational again as quickly as possible. And we do that by applying the let it crash concept. We let a component fail, and we delegate on the supervisor the management of that failure. We also do that by wrapping up the notification of the failure inside a message, because our system should be message driven. We place a big deal of effort into testing, and we do that to understand the level of damage a failure can inflict on the functionality we are providing. We don't use every tool and solution at our disposal. We just pick the right one, the one that will make our system responsive again faster. We notify the right supervisor. In most cases, there's no point propagating details of the failure to the end user. And the other side of the coin could be the use of defensive programming, let's call it that, where we tend to use a lot of like try catch statements in the code, a lot of conditions and branches to prevent our system from failing. But as we stated before, that kind of control is just an illusion. We're just writing expensive code. It'll be hard to debug, hard to maintain, and hard to scale. We can also agree that the level of damage a failure can cause is usually as bad as our lack of component autonomy in the system. A failure in a component must not affect the other components. Each component needs to be isolated in a way that failure does not incapacitate it. So it needs to be observable, both in space and in time. That's why we need to do an effort of decoupling in these two different dimensions. Decoupling in space is as common in systems with blocking communications as to the non-blocking ones. We are already concerned about providing isolation, providing layers of abstraction that makes the system elastic, meaning that if we have multiple consumers, they can be bound to the same virtual address to receive messages, and that allows to the failure to be kept inside designated failure zones. But coupling in time, this is where the reactive approach kicks in, or the non-blocking approach kicks in, because it enables other components to communicate without actively waiting for a response, and then reliably detect and handle failure even when they cannot be explicitly communicated. And now that we have reviewed some of the most important concepts, let's see what are some of the common strategies to make our system more resilient to failure. We have retry. Something went wrong, but let's try again. we have fallback or graceful degradation when something went wrong. But let's provide a default value instead, or let's provide a nice way to explain what went wrong to the user. Timeout. We are not letting a request or a process exceed more time than whatever we know it's normal. Circuit breaker, which can be activated when a component is constantly failing, and then the circuit breaker will just prevent any more calls until that failing component gets back on its feet. Rate limiting, where we provide a limit of events or messages or requests that we consider reasonable for a given resource to handle within a short span of time. Back pressure. This is one of the key mechanisms of reactive systems, because with back pressure, we can identify a component down the chain being unable to keep up with the rate of the input. So this component might be too slow to process the volume of the incoming requests. And thanks to back pressure, we can make the clients aware that it needs to start buffering events to slow down the rate of requests being sent to that stressed component. Load balancer, which is the effort to distribute traffic across different instances of the same service to prevent overloading any of them. And bulkhead. Here, we provide copies of services that were meant to be reusable across like a vertical cluster of different capabilities. So this way we are further decoupling components in space to help isolate those areas of failure. But this particular approach comes with different trade-offs that must be considered, such as the capacity of our platform to scale like a significant number of these copies. Yeah, so all of these and much more are effective tools to handle different kinds of failure and be prepared for when components in our system start crashing. So let's go over this quick example of how we can implement some of the strategies in our system, or where are the opportunities to use them. So we have our system, and we have this API that interacts with 3 third-party services, and it does this through a gateway. And after a while, we start noticing that the nature of the failures that are happening in the system, and we can fix our own points of failure within our system, but we cannot fix the third-party services. But we can prepare for them. We can make our system resilient to the failures they usually produce. In this example, we can see that the third-party service number 1 sometimes takes too long to respond. So we can set up a timeout for that service. We can also see that the third-party service number 2, it gets easily overloaded. So we can set up a rate limiter for that service. And we can also see that the contract of the third-party service number 3, it tends to change without the vendor properly notifying us. So we can set up a circuit breaker, for example, for that service, so that the moment we're constantly getting that request responses, we can just stop sending requests to that service. We know that it's going to keep failing. Let's see. Okay, another example. This time, I wanted to illustrate how we can use the message-driven approach to prepare for failure. The dotted lines in this diagram represent time, and we have 2 different systems. The one in the upper part is a system that is a traditional blocking system of a client that sends a request to a service and waits for a response. The one in the lower part, though, is a client that pushes messages to a queue and a service that pulls messages from that queue. So in the first system, when the service fails, the client will have to wait for the service to be back up again. They are kind of bounded to each other that way. But in the second system, when the service fails, the client will just keep pushing messages to the queue and the service will process them as soon as it's back up again. So the key thing about what happens when the service fails is that in the first approach, request number 3 and 4, they will fail and the service will not be able to process them. But in the second approach, messages 3 and 4 are queued and the service will just process them as soon as the service is back up again. So as you can see, we have decoupled the client for the service from the service in time. Okay. Sometimes teams will question the worth of turn traditional REST APIs into non-blocking services. And we can see the value of doing that for writing operations, but maybe the benefits are not so evident when it comes to queries, when it comes to reading operations. And the right answer, I guess, would be to evaluate this in a per case basis. Sometimes it will make sense, sometimes not so much. But generally speaking, on paper, some of the benefits of choosing the non-blocking options are the fact that services make more efficient use of the resources. They perform better in terms of latency. They have easier and deeper control over error handling. And they definitely have more control over the flow of data using mechanisms like back pressure, as we explained in a previous slide. Okay, so I wanted to use this next slide to just briefly highlight the role of observability in a system. We need to be able to observe our system in order to be able to react to failure. We need to know what happened. We need to know when it happened and where it happened and why it happened. We need to pinpoint the reasons and where exactly in our system the failure happened. And those diagnostics will help us build and scale truly resilient systems.
Gonzalo, do we have a question in the chat?
Oh, sorry.
Do you prefer to do the question at this going, or do you prefer to answer all the question at the end?
Yeah, no, let's hear it. Let me pull up the chat because it suddenly disappeared.
Yeah, well, Luke was asking is, are there any downsides in the no blocking system?
There are downsides in the no blocking system. It's something that is you really need. It's like I said, this you need to have to go into a per case basis and see if it's right, because turning REST APIs, let's say that you have a traditional API that is just a CRUD service that performs CRUD operations, and you might think, why would I need to turn my services onto non-blocking? The first kind of I don't want to say like wall or barrier, but in my experience, it's a very expensive process to turn this, to make the conversion, just because people are just not used to it. They find it, for example, hard to debug, which is something that I am not totally agree, but I can see why they say that. It happened to me. It's you suddenly see yourself need to understand not exactly where your events or your messages are, but when are they. You have to introduce the concept of time. And for teams, especially if they have backend background and more specifically Java background, that conversion is hard to do for some developers. It takes some time. The learning curve is a little bit steep. So that alone is a little barrier right there. And in terms of performance, if your question was more about performance, you do need to, you will find yourself needing to tweak sometimes the rates of, or better to say, you need to analyze how you're going to receive your data. And be aware that in order to make a fully non-blocking, let me go back to the slide actually. In order to make a fully non-blocking chain, all the components in that chain needs to be non-blocking. Otherwise, you are blocking somewhere, and then you will never get the benefits, the true benefits of a non-blocking system. So you need to have all your components ready to be non-blocking, and also you have to need a driver. This example, for example, this example takes the data from a database. You need to have a database that is non-blocking friendly. You need a driver to access that data with that kind of input-output operations. Does that answer more or less the question?
Yeah, I just was curious because I know when you're doing writes in a non-blocking way to like a database, that seems like you could run into the problem of, you write some data, but what happens if you try to read that data and it, all that kind of timing of like, well, how did you actually write it? And how do you make sure that it's written? Because if it's not blocking, you might be trying to do a read before the write's finished. And so there's always that kind of,
that's fair. I guess that's a trade-off. If that's the case, you might want to design or make the decision from the drawing table when you are designing the user experience and see how it all will fit into your non-blocking system. But know that, and you guys might have heard about this when it comes to pulling data in non-blocking and also blocking, I guess, there's this thing called eventual consistency. That's kind of what is going to ultimately guarantee that the data will be there and will be updated at the same time. It all depends on the use case and how, when you want the data, how critical is that you access the data in the right moment or not. So you have to consider all those scenarios, like I said, kind of from the beginning when you're designing the user experience. And from there, you will be able to start seeing patterns of, okay, it makes sense if I do like more like a real-time experience. So I'm constantly pulling messages from a queue, or hey, maybe I just need like a huge list of things all at once. So there's really no need for a non-blocking approach in here.
Yeah. It definitely sounds like it's situational. Like it really depends on what data you're talking about at what time. And
it really does. For me, I would say that designing your services non-blocking is it's easier to just roll back or manually block whenever you want. But if you have a traditional blocking backend set of services, you like the cost of turning all that into a non-blocking, it's way more expensive, if that makes sense.
Yeah. Thank you.
Yeah, no problem. Let's see if there's any other questions. Okay. So yeah, we went over observability. Some of the, like, there's of course like a million more of observability tools that we can use. I've just illustrated a few of them. And oh yeah, the case studies. So this case study, to wrap up this talk, I just wanted to present these 3 different cases. They are public cases. You can search for the details on any of these online, but I'll just give you a brief summary on them to kind of connect the points that we were talking about during this talk. So the first one would be the Night Capital 2012 trading glitch. So Night Capital, this is a major financial service firm, and they experienced a software glitch in 2012, and that had like devastating effects. A failure that after a software update, it led to the system malfunction, like a flood of orders to the market. So the firm lost around 440 million in less than an hour before they could halt trading manually. But nothing technically made the system fail or crash. It was fully functional, but the lack of like a fail-safe protocol prevented this erratic behavior from being stopped. So the lesson here is, if I have a process constantly doing something wrong, I want to stop it. I would rather have it fail and crash, right? Otherwise, we are just letting it self-heal, or in this case, just doing the wrong thing super fast. And the impact of that was, like I said, devastated for the firm. Some of you guys might remember the Amazon Prime Day outage. So on Prime Day back in 2018, so at the peak of customer demand, the Amazon website crashed. Not really crashed, but a lot of the functionality just start to not function properly. So users experienced difficulty logging in and received error messages, and faced issues with item searches and transactions. This issue lasted only, it was for only a few hours, but given the scale of Amazon's operations and the volume of transactions on Prime Day, you can imagine that the losses were significant. The cause of the outage was attributed to a failure in the Amazon's auto-scaling capabilities. So this auto-scaling feature was designed to accommodate sudden spikes in traffic by automatically adding or removing resources as needed. However, the surge in traffic on Prime Day was so intense that this auto-scaling setup failed to work properly, leading to the crash. So in response to this failure, Amazon just had to swiftly add more resources to relieve the massive demand. But they did what was necessary. Even well-designed systems will fail under certain conditions. But they did what was necessary, and this is to stay responsive. That was the key for them, to offer the ultimate, to not offer the poorest experience of all, which is just latency issues, or that those are the experiences that make the user exit. a website or a platform. So they knew that whatever they do, whatever component was failing, would need to be isolated and then use replication or whatever protocol in place they have to stay responsive. And this is, the next one would be, I think, the most interesting case of all. So Netflix developed, a while ago, Netflix developed like a suite of tools. They are known as Simian Army, to proactively introduce failures into their systems to ensure resilience and high availability. And a famous tool among this is Chaos Monkey, which randomly terminates instances in production to ensure that engineers implement their services to be resilient to this instance failures. So while it may seem counterintuitive to intentionally create failures, this strategy really allows Netflix to constantly test their systems in real world conditions and learn from the weaknesses found. So embracing failure in this way has led to the creation, you could argue that embracing failure in this way has led to the creation of a more robust and resilient system capable of maintaining function, even when parts of the system fail. Okay, so yeah, in conclusion, failure, oh, sorry, that's my light right now. The only thing that provided light, because in Pittsburgh is nighttime. Anyway, failure is not the end, but rather like it's an opportunity to learn, to adapt and build more resilient systems. So yeah, thanks for your attention. Let's use a few minutes to see if I can answer any other questions you may have. Okay.
Yeah, I think it's great. We'll let people kind of sit for a minute and see if they have any questions. But I'll start off by just saying thank you so much, Gonzalo. This has been really interesting and just really thought-provoking about, how do you handle failure? I'm used to it. I'm used to having lots of failures. So like, but like in computer systems, yeah.
Right. Like most of what it's been said here, you can apply to like real life. Hey, failure is everywhere. We are not perfect, and we crash. So we just
not a matter of if, it's a matter of when.
Exactly. So yeah, in software, it's basically the same thing. There's no such thing as a perfect system. So the better prepared we are to handle the failure, the better. That I guess that kind of was the point the guys that wrote the reactive manifesto were trying to make. But yeah, thanks again, guys, for having me. Oh, there's a question about the slides with back pressure. Oh, okay.
Hi, I'm Nicole. That was a very nice talk, by the way. Thank you for sharing those slides and everything. So I have a question about the back pressure and the load balancer. I'm familiar with how a load balancer works, that you have some sort of software or some sort of server or something that will direct traffic to your services. But with the back pressure, it seems very similar to a load balancer when I look at the slide. I haven't worked with something with back pressure. So I was wondering if you could explain that a little bit.
So back pressure, it's fair. Back pressure is one of those things. Give me a sec. I'm going to just turn on a light here because
You don't like being in the dark. I get it.
There we go. Sorry about that. Back pressure, this is fair. It's really, it was a mystery to me when I started learning reactive, because it's hard to explain where exactly happens. But what you need to understand about back pressure is that it is all about the communication between to services that are non-blocking or kind of message-driven friendly. Let's say that. And in this case, in this diagram, I wanted to illustrate the problem. The problem is that you may have a producer that is sending data too fast or fast enough for the consumer to not be able to kind of process it. Let's say that you are receiving messages at a rate of 500 milliseconds, and on the other hand, you have a consumer that, yes, it is able to process that, but after that, each message that it consumes, it needs to process it again, and let's say that takes 1 second. So the consumer is not able to keep up with that kind of input. So when we establish back pressure, it's kind of like a shake of hands between the producer and the consumer, saying, "Hey, thanks for the data, but I am too slow. You need to give this to me at my own rate. So I will tell you when I'm ready for the next message."
Okay, that makes sense now.
So the fast producer will say, "Okay, here's your item, here's your event, your message. Like I'm fast, and I can give you this at my rate of 500 milliseconds or whatever. But I understand you cannot handle this rate. So here's an item," and then the consumer would say, it will produce it, do whatever process it needs, and then it will send a signal to the producer saying, "Hey, okay, next one." And so the consumer will be one
ready to take,
but will establish the rate here,
right?
So that it doesn't get overloaded, and because otherwise it will just start buffering events, and eventually the memory will just explode.
Yep. Okay, you explained it very well. Thank you.
Yeah, no problem. Okay, let's see. Oh, the load about the load balancer. Yes, it was basically about the component that you described is something. It's a piece that we put in place between same instances of the same service, usually to prevent overloading any of them. So it will just, let's say that there's a client in which we are kind of producing all the traffic, and it gets to the load balancer that kind of, it usually lives within like a gateway or any other kind of server. And that's where it will route to whatever instance they know to be more available, if that makes sense. Okay, loving the case studies. It has been, oh, okay. But would you recommend some book for read about these topics? I don't think I've read any books about this topic. I did read a lot online. The first, if you want to go into the reactive world, I think the first place to go is to go into the reactive manifesto. You can search for that. You can just Google it, and the first result will be this reactive manifesto webpage that was written by some really brilliant guys, in which they describe all of this way better than me. And not only failure, which was this topic, but all of those kind of principles and rules, they go with a lot of detail into each one of these. There we go. That would be the link. And if you want to learn about failure or how to better handle errors and things like that, Nothing on top of my mind, but I guess there are a lot of reading material in books like Clean Architecture, where this gets tackled in a lot of ways about how we provide isolation and decouple components and all of that. Let's see. Okay. Well, now that I have more light, I can go into the last slide to give you guys a couple of links to reach out if you want to if you have any other questions, or if you just want to connect. So yeah, thanks again to all the Dallas GDG group, and I hope this has been helpful.
Yeah, sure. Thank you, Gonzalo, for your talk. It was super interesting. It's a topic that sometimes you don't think so much about it. You just used to code to be perfect, not waiting for the failure, and yeah, shit happens, right? And I am sure that happens to all of us in different ways that you never thought, and in the worst moment. So yeah, that's Murphy laws, right?
Unfortunately, we learned
yeah.
the wrong way, or the hard way.
Yeah, that's true. Well, yeah, it was great having you, and yeah, feel free to reach out again if you want to talk about this topic or any other thing when you want. So that was a pleasure to having you, and thank you everybody to join. I hope that it was nice and you learned something today. Thank you.
Thank you so much.
Thank you.
Yeah.
Ciao.
Thanks, everybody.
Thank you.